Welcome to part 2 of types of chemical reactions. In the last video, you talked about the first 3 types of reactions: synthesis, decomposition, and combustion. And in this video, we are going to cover the last 2, single and double replacement. And before we proceed with this video, you should know that none of the equations that I'm using in this video will be balanced, because I want you to focus on what's happening in the chemical reaction as opposed to the coefficients that are in front of the chemical compounds. All right, so let's start with single replacement reactions. I numbered it number 4 because it's the 4th type of chemical reaction I've talked about. The first 3 were in the first video. So this little drawing is supposed to help you know what's going on with a single replacement reaction. So in a single replacement reaction, you have a single element, and that single element is going to kick out the element that it is like in a compound and take its place. So in this case, C is replacing or kicking A out of this compound, and then ultimately ending up with B and then leaving A all alone. And so I don't know if you noticed that in my definition I said that a single replacement reaction is when a single element replaces the element that it is like in a compound. So what I mean by that is the single element, if that single element is a metal or a cation, it is going to replace the metal or the cation in the compound, because cations are like other cations, so metal replaces metal. Or if that single element is a nonmetal or an anion, then it is going to replace the anion in the compound, because nonmetals are like other nonmetals. So let's look at this example here. I've got lithium, and we're adding that to potassium chloride. Lithium is a metal, and so it is going to attempt to replace the potassium in this compound because the chlorine's a nonmetal and lithium's a metal. So lithium's going to replace the potassium because they're both metals. And so what's going to happen is lithium will come over here and actually kick potassium out of the compound. And you'll end up with lithium bonded to chloride, and then potassium will be left all alone. Now, there's a thing called an activity series that you will be given in class. And an activity series is a list of metals from strongest to weakest, or we like to say most active to least active. And as you go down the list, the metals become less and less capable of replacing the metals above them. So if you find lithium on the list, lithium is above potassium, which means that lithium is capable of replacing potassium in this compound. So an activity series is something that you will need to check prior to predicting the products of a single replacement reaction. Whatever the metal is that's the single metal, so in this case lithium, it can only replace anything below it, not the things above it. So for example, if I had something like this, we've got manganese and we're putting this or reacting it with calcium oxide. So before we want to go write products, we need to go check our activity series. And we see that manganese is right here and calcium's above it in the list. So manganese is a metal and calcium's also a metal. The problem here is that manganese is below calcium in the list, which means it's weaker than calcium. So even though manganese may want to come over here and attempt to replace calcium, calcium's too strong. And so you're not going to get a reaction in this particular instance. So before you go predicting the products of a single replacement reaction, you have to check the activity series to see if it will actually happen. So what if our single element is a nonmetal as opposed to a metal? Well, that single element isn't going to want to replace the metal in the compound. It's going to want to replace the nonmetal. Don't forget, by the way, F-fluorine is a Brinkelhoff element. So remember the Brinkelhoff nonmetals are those that need to be diatomic as opposed to single atom elements. So you'll notice that these are metals on our activity series, not nonmetals. And since this fluorine is a nonmetal and so is bromine, we need a nonmetal activity series. Rather than giving you a list, I am going to make this easy. So on your periodic table, the only nonmetals that I'm going to have you know the activity of are your halogens. That's family 17. And their activity is in the order that it's given on the periodic table, meaning that fluorine is the most active, and then chlorine, then bromine, then iodine, which means fluorine can replace anything below it in the family, or chlorine can replace anything below it, but not anything above. So fluorine is above bromine, which means that it's capable of replacing the bromine in this compound. So our fluorine is going to come over here and kick out the bromine. And we're going to end up with, on the other side, of course, our bromine all alone. And remember, bromine is a Brinkelhoff element, so it can't be just Br, it has to be Br2. And then to write the formula for the compound, you know that the cation is going to go first, and sodium has a +1 charge. Fluoride's an anion, and it has a -1 charge. So you just need one of each of those in your compound. So, of course, there are 2 fluorines because when it was alone, it was diatomic. But once it turns into an ion and joins with sodium, only 1 fluorine to 1 sodium. So that means that we would then have to go back and balance this equation to make it work out. I fully expect you to be able to predict the products of a single replacement reaction. And so you need to make sure that before you write down the products that you check the activity series to make sure that it's actually going to take place. All right, let's try an example. So here we have aluminum and iron chloride. And if we put aluminum into iron chloride, is a reaction going to take place? Well, let's identify what we have here. We have aluminum, which is a metal, and then we have iron chloride made of a metal and then a nonmetal. So aluminum, being a metal, is going to attempt to replace the iron, which is also a metal. Now, before we start writing products, let's go over to our activity series and find aluminum and iron. So aluminum is above the iron, which means it's stronger than the iron, more active. So indeed, it's going to replace the iron in our compound. By the way, if it wasn't going to work out that way, if it wasn't above the list, you would just write no reaction, like I did up here. But in this case, we're going to get a reaction. So to predict our products, we know that the iron is going to be left all alone. That's easy. And iron's not Brinkelhoff. None of the metals are, so it's just Fe, iron. However, we need to look at charges on our aluminum and our chlorine. So aluminum has a +3 charge, and chlorine is a -1 charge. So because of those charges, and because we're making an ionic compound here, we need to cross the charges down and end up with AlCl3. And then, of course, you can go back and erase the charges because they've canceled out. So there are the products of this single replacement reaction. All right, so we're at the last type of chemical reaction here. This is called a double replacement reaction. Double replacement reactions are really nice and easy. They don't require an activity series like single replacement reactions. And they're pretty straightforward. So generally you will have 2 ionic compounds, and what happens is the cation in one ionic compound will actually switch places with the cation in the other ionic compound. So in this case we have A and B hooked together, and then C and D in a compound, and the A and the C just switch places. So the A ends up with the D, and the C ends up with the B. So they just swap places. So something like that would be taking, say, lithium chloride and sodium hydroxide. The lithium and the sodium are your cations, and they're just going to switch places. Now, the trick, of course, becomes when you're writing your formulas, you are dealing with ionic compounds, so you're dealing with ions. So you actually have to look at the charges on the ions. So lithium is going to end up with hydroxide, and then sodium is going to end up with chloride. And you're going to want to check your charges and make sure that you write the correct formulas. So it turns out that because lithium and sodium are both +1 charges, they can just directly swap with one another. So you end up with LiOH and NaCl on the other side. And of course, hopefully you remember, you're supposed to just go back and erase your charges. So I fully expect you to be able to predict the products of a double replacement reaction. We're just dealing with ions and ion charges, so it should be pretty easy. All right, so let's practice a little. So we know we're going to get two products here. In fact, the only kind of reaction that you won't get two products in is a synthesis reaction. In this case, we're not doing synthesis, we're doing double replacement. And you can tell because you have two ionic compounds. So you know that the cations will swap places, which means that the potassium and the silver are going to switch places. So on the other side, we know that the silver will end up with the sulfate, and we know that the potassium will end up with the bromide. So the trick becomes looking again at the charges on these ions to make sure that you write the correct formulas for the compounds. So silver is a +1 charge. It is a transition metal, but it's one of those that has a set charge. If you should forget that, though, you can look at what it's bonded to right here. Bromine has a -1 charge, and there's one silver bonded to it, so that silver must have a +1 charge. Sulfate has a -2 charge, and potassium has a +1 charge. So if we look at the two formulas, silver and sulfate, there should be two silvers bonded to our one sulfate. And then our potassium and our bromine have exact opposite charges, so we just need one of each of those. All right, so that brings us to the end of my presentation on single and double replacement reactions. And if you want to or need to, you should go back and watch part 1 and then part 2 again so that you know all 5 types of reactions.